Hi, my name is Maciej Trzeciak, and I am a PhD student at Cambridge. Professor Ioannis Brilakis is a co-author on this paper, and and this presentation is about mobile 3D reconstruction and how to improve precision there, and density. So just to motivate my work, digitizing the geometry of buildings is, as you know, a key element for many use cases in the AEC industry. However, data acquisition using static laser scanners or photogrammetry methods is lengthy, and it requires even lengthier subsequent processing. And quick and apparent escape from this problem might be mobile, especially handheld mapping solutions, which are mainly based on LiDARs, so those sensors here. However, the current state of practice, mobile mapping devices do not allow for scanning with high resolution. So the resolution is the key here. Therefore, it is not uncommon that there is a mix of static and mobile scanners on construction sites depending on the requirements of the use cases at hand. So just to give you a note on the precision and accuracy in mobile scanning, so let's look at this image for a moment. So we talk about high accuracy when on average points, the average location of the points is correct. So for example, here is high accuracy, but also here is high accuracy because on average those points are in the correct location. However, when it comes to the precision, those points have low precision because their spread is big. And for example, here the spread is low, so the precision is high. And also here we have a situation when accuracy is low, but the precision is high because this spread is low. So in other words, mathematically, the standard deviation is small. And now when we can see such a situation in real life. For example, here is a scan from a mobile scanner, and here is a scan from a faro scanner, so a static scanner, right? And we can see that if the noise or the precision is very high, we also have colors and the point cloud is dense, then we can very easily recognize that, for example, here is a door, there are some geometric features like edges and corners, whereas in this scan, we can barely see anything. So my paper focuses on precision, density, and colorizing the point cloud, and those three features, I believe, are the main features of high-resolution point clouds. All right, so my method is focusing on improving resolution, so not accuracy. So my method is applicable for such handheld scanners, which consists of camera and the LiDAR. And so basically, the input is a stream of color images and LiDAR scans, and the first step is data preparation. So the thing is that a camera and the LiDAR, they do not know about each other. So they basically send messages. So each image and each LiDAR scan, I will call them a message, and those messages are sent asynchronously. So they don't know about each other. So the point here is to synchronize them in time, and I do that through standard techniques in robotics, where each message is time-stamped, and if the difference in timestamp is smaller than a certain threshold, then I consider such messages to be time-synchronized. And in addition, we need to spatially register images and LiDAR scans so that they give me geometry-consistent signal. And this is done offline through something which is called camera-lidar extrinsic calibration, where basically the point is to estimate rigid body transformation between coordinate system of the camera and the coordinate system of the LiDAR. And once I have this transformation, I can, for example, project LiDAR points onto the camera space, and vice versa, I can project pixels onto points of LiDAR, and this is how basically colorizing of point clouds happens. So this is the data preparation step, and now actually I will start talking about the core steps in my solution. So the first step is this camera-guided increase of LiDAR's resolution. So the point here is to use some deep learning techniques based on images to predict certain features on images which give us additional constraints on the geometry of the scene. So they will give us, I will be talking about this in a moment, but they will give us more geometric information so that later in the optimization process, which will increase the resolution of the LiDAR, we can actually improve this resolution. And once we have those high resolution single viewpoint clouds, we can stitch them together in an odometric manner. So actually this stitching together point cloud is called odometry, and because it is 3D reconstruction, so I named this odometric 3D reconstruction. And the output of this process is basically a static accumulated point cloud, which can be then post-processed. So by post-processing, I mean removing outliers or downsampling point cloud, all those things you can do there. But everything that you will see in this paper is just based on those first three steps. So I didn't do any post-processing here. Yeah. So you know, I will not describe the whole pipeline in detail because it's quite a lot of things there, but I just want to give you the intuition behind this method. So I was talking about those additional constraints that we can predict from the images, right? So there are two neural networks there in my system, and those two neural networks predict surface normals and occlusion boundaries. So here you can see the surface normals, and here we can see the occlusion boundaries. So obviously, surface normals, when you have a surface, you want to predict a vector which is normal to the surface. And this is what is done through one neural network, and the other, maybe less common in the construction industry, are occlusion boundaries. So what occlusion boundaries, we really want to predict three classes there. One is the red one, which is a boundary itself, so this is like a surface. When there is no geometric discontinuity of any kind, then we basically want to predict this pixel as a surface. If there is some discontinuity, for example, in green, for example, here you can see there is a small green area. This is depth discontinuity. When we have one object and the other object, and we know that they don't touch each other, and the camera took a photo from, let's say, this position, then we want to predict that there is no real boundary between those two objects, and we want to predict this as depth discontinuity. And there is one more class marked in blue, which is normal discontinuity. So, for example, if you have an edge, here normal vectors point towards you. Those vectors point towards the screen, and there is clear discontinuity. And we also want to predict such a situation. And now, having those two dense feature maps and LiDAR points in the form of sparse depth maps, we can use standard optimization techniques like nonlinear least squares to basically densify those sparse points, and as a result, we will get this dense, very dense LiDAR depth map. So just to give you a clue how much density is increased here, the coverage of pixels here is just 2%, whereas here we have 100% because we do this optimization for all the pixels in the depth map. And then, because the camera is calibrated, so we can back project those depth pixels to 3D space, and this is how we create single viewpoint clouds. And then those single viewpoint clouds, as I said, are stitched together in an odometric manner, and this is how we create a static point cloud of a scene. So to implement my method, I built such a prototypic scanner, which consists of a Velodyne VLP16 LiDAR with 16 beams, and the camera, this is a standard lens color camera. And I wrote software for this method. So what you see here, for example, is a stream of images that this camera sees, And here is a stream of LiDAR scans, which are already scene referenced. And when you put those two streams of, when you put those two signals through my method, then you will get such a very, very dense reconstruction, which is even hard to distinguish from an image because its resolution is exactly of the resolution of the camera. And when you do this scanning fully, that will be the outcome. And I compared, so let's first talk about qualitative results. This column is the reconstruction from my method, this is the reconstruction from Google Tango, and this is the reconstruction from LOAM. So LOAM stands for LiDAR odometry and mapping, and basically, when I was doing those experiments 2 years ago under the most stringent COVID restrictions, so LOAM was the best generic LiDAR-based 3D reconstruction method. And so when we see, for example, let's take this door of the wardrobe for a moment. We know that this door should be flat, right? So when we take a look at my scan, indeed, this scan is flat, whereas from Google Tango it's a little bit bumpy, and in LOAM it's very noisy. Then let's take, for example, this void between those two pieces of furniture. In my scan, it is quite well pronounced. In Google Tango, those two pieces of furniture are actually glued, and in LOAM, again, it's quite noisy. And when we look at the handles of the drawer unit, they are also slightly better pronounced in my reconstruction. They are basically crispier. Here are less crispy, and in LOAM, we cannot even see them because of the noise level. And now when we jump into quantitative results, so again, I did a very simple analysis. I literally took a part of this door of the wardrobe. I extracted this point cloud from my reconstruction and the reconstruction from LOAM. And in this part of point cloud, because we know that it should be flat, so I basically fit an ideal plane there and measure the distances between individual points and this ideal plane. And when you now make histogram out of those distances, so that will be the result. And the red histogram represents the spread of, represents the distances from LOAM. And as we can see, if you want to cover 95% of those distances, they will be in between plus minus 30 millimeters. Whereas in my method, those distances will be within plus minus 10 millimeters. So it's 3 times improvement. And in addition, the density in my reconstruction is around 5 times higher than in the reconstruction by LOAM. So these 3 facts, that the noise is lower, there is higher density, and I transferred this color information from the camera on the point cloud. So then those facts can make me cautiously conclude that my method can increase indeed the resolution of point clouds. So just to summarize, in this paper I showed a new 3D reconstruction pipeline for handheld scanners with the goal to increase the resolution of point clouds. In an indoor experiment, I obtained relatively denser and more precise point clouds with a 67% reduction in noise of reconstructed planar surfaces compared to LOAM. Then you get this colorizing of point clouds by default because I do this camera-lidar fusion. Potentially, my method can unlock use cases which so far have been unreachable by mobile scanners because you can decrease this noise level by 3 times. And the drawback, obviously, is that there are 2 neural networks there, which require quite a lot of computational cost, which is kind of hard to get on mobile devices, which have very limited resources. And the future, let's say, extension of this paper would be to do experiments outdoors, ideally on a construction site. And on the final note, my research received funding from BP, GeoSLAM, Lenge O'Rourke, Topcon, and Trimble, and I would like to thank these companies for making my research possible. And with that said, I would like to thank the audience for listening, and I'm happy to answer questions. Thank you.